Every advanced product you use today, like a vehicle, a smartphone, or a robot, is an embedded, integrated, complex system. But no system starts out that way, and complexity is usually not something that was planned on the beginning of developing such a system in the early stages. It grows every new function, every new component, and every new release. Almost every system starts purpose-built unit, which means one hardware, one software, and one specific function. This is the classic embedded system. In hardware, running a specific software, for example, a small controller or a sensor module. It is optimized for its task, so it works with limited resources and a deterministic timing behavior. And at this stage, the whole behavior is still easy to understand. You can usually test such a unit as a whole, because at this point, everything is still simple. Products compete on functions, so new features get added with every release. Each new function then pulls in a new component, for example, additional sensors, controllers, displays, or connectivity modules. These components come from different teams, different departments, and also maybe from different suppliers. Together, they form an integrated system, which means multiple interrelated parts that build the whole system. And each part might still be simple on its own, but the assembly of all parts is not. All these components have to work together, and they do that through interfaces, protocols, and shared resources. The number of connections grow much faster than the number of components. With 5 components, you have up to 10 possible links. With 10 components, it is already 45. But with 20 components, you're close to 200. Of course, you might not use each of every connection in a real product, but it shows how complexity can be created. Also, a change in one unit can propagate to many others, because the components depend on each other. So the overall behavior arises from the interactions and cannot be reduced to a single component anymore. That is the point where you have a complex system, and no single view explains the whole anymore. A complex system also never stands still. Then you have product variants, so one product exists in many configurations for different markets and hardware revisions. Hardware and software evolve at a different pace, which means their releases are often not synchronized. Then there are continuous updates, so the system is never really finished. And the ownership is also distributed over many component managers, which can have very divergent interests. And of course, old parts remain in the system while new parts arrive, so legacy adds up over time. For quality, this has very practical consequences. Failures often originate between the units and subsystems, and not only within them. So component-level testing alone cannot ensure the end-to-end quality of the system. The interaction of hardware and software has to be validated under real conditions, because timing and environmental factors may affect the system. Cross-domain functions like security, connectivity, or storage also need to be validated jointly. And with responsibilities distributed over many parties, you need an overall authority for quality assurance, which is the role of system test. So this was a look at how systems get complex and why that matters for testing. So to summarize, complexity is the natural result of growth, with more functions, more components, and more interactions. Failures in complex systems usually originate between the components, not only within them. And you cannot prevent complexity, but you can manage it with structure and end-to-end testing.